Alright, next up, let's talk about forming those three-membered rings one more time. I promise this is the last one for the chapter. This time, cyclopropanes. Now we have a problem. If you remember what we've done in the previous chapter and in the previous topics on this, we need basically an atom to act both as nucleophile and electrophile to manage to form a three-membered ring, either stepwise or, in the case of the epoxidation, simultaneously. So visualizing how we might do that with carbon is a little bit odd. There are a couple of different ways to do it. The first and most well-known is something called diazomethane, so CH2N2. Now, if you try to draw a Lewis structure for that, you're going to realize immediately it's a little strange. Basically, it's going to come down to something like this. So that we're really going to have some problems being able to draw this cleanly without having some obvious things happening here. So we're going to have a positive charge and a negative charge adjacent to each other. That's called a Zwitter ion. That's called a positive charge and a negative charge next to each other. That's called an ylide, Y-L-I-D-E. But more specifically, something that you should notice now, because you're going to see it several times throughout this course and the next one, is when I have two nitrogens bonded to each other, it is almost a certainty that they're going to end up as N2 gas eventually, some way, somehow. In this case, you don't have to look real hard to figure out how. All I need to do is break the bond between the carbon and the first nitrogen, and I have nitrogen gas. So, one, that makes for something that's very clearly reactive. Two, it makes for something that's very clearly dangerous to handle, because it's going to readily give off a gas, which means its volume will expand very, very rapidly. And if you're doing that in a flimsy flask, well, you're about to find out whether you like glass cuts or not. So it is something that requires some care in handling. This is a particularly nasty reagent, but for demonstration purposes of how this is going to work, it makes perfect sense. Generally, it's thought to work like this, that we end up in the presence of either ultraviolet light or heat, probably not one I would choose, or a catalyst, sometimes like copper, severing this. So basically, this bond breaks towards the other nitrogen. Well, that's going to give me my nitrogen gas. Fine, good, as long as I have a pressure vent, that's fine. Which is the only real hazard here, is if you're going to build up a gas pressure, have a way for it to get out. The other piece is a little bit odd. This is a strange customer. Now, you will notice a couple of things. First, there is no formal charge here. That carbon is neutral. It can claim the same 4 electrons that it can in its atomic state. But it is a violation of the octet rule, so it is a very reactive, although not formally charged, species. This is called a carbine. And if you look at it, you're going to notice there's a problem. In that where that bond to the nitrogen was, there was an orbital there. It was a hybrid orbital at the time. Well, now it's still there. It's empty. So this particular species has both an empty orbital and a pair of lone pairs, a lone pair of electrons filling another orbital. So I have something that is basically sp2. So I have a pair of electrons here, and I have my 2 hydrogens in and out of the plane, and above and below the plane I have an empty p orbital. So basically you can think of this as having a nucleophile and an electrophile on the same atom, which is exactly what we need. It's actually a little simpler to see that way than it was with the epoxidation that had a more complex reagent with a lot of arrows going on when this happened. So basically, my alkene is going to act as a nucleophile towards that empty orbital, and that lone pair is going to act as a nucleophile towards one of the atoms of the alkene. So it has to be syn because it can't reach around to be trans. It's impossible for something to react at the same time on two different faces of the alkene without being a prohibitively large structure, and this is one atom that's reacting, so not prohibitively large. Generally speaking, though, diazomethane is a little bit more than most people would like to handle. It is a little problematic. We can make other diazocarbon species to make a different cyclopropane, so having something other than these H's here would give me something other than those H's here. So that's a little bit easier to do because the diazoalkane would not necessarily be a gas, whereas diazomethane is. So it's a little bit more difficult to handle than we would really like. More commonly, we'll see a variation on the theme here called a Simmons-Smith reagent, and it looks like this. We'll basically have something like diiodomethane, and it'll be treated with zinc. And if we do that, so if I have something like this, and zinc metal, what I get is basically a stabilized version of the same carbine problem. Is I'll still have my two hydrogens, so I'm going to get the same product out of this if I use this instead of diazomethane. But in the one case, I'll have an iodine, a leaving group. You knew that was coming back at some point, right? And in the other case, what happens, and we'll use this a lot later on in this course and the next one, is the metal inserts itself into the carbon to halogen bond. So I end up with a metal here, if I drew it as all covalent like this. Well, this is a leaving group, which means that carbon is acting cationic because of that. That is the sort of equivalent of that empty orbital. It's going to react as the electrophilic site. Here, though, zinc is less electronegative than carbon, so carbon has a better grip on these two bonding electrons. So this is going to basically be the equivalent of that lone pair of electrons. So if I did the same reaction here, taking the Simmons-Smith reagent, this combination of the diiodomethane and zinc metal, put it together with those, I get exactly the same cyclopropane out of it under what would generally be considered a little bit safer and simpler conditions for most people to handle. So preferable, definitely more scalable. You wouldn't really want to be handling questionable safety reagents on a very large scale. It's still done, but not my favorite thing to do. Last, there's other ways to get to carbene species that are useful. They're not necessarily going to be two hydrogens on them, but one of them, which comes up quite a lot, is chloroform. Now, this has been around a long time, and I'm just going to draw a Lewis structure without trying to do geometry here, as a solvent as well as originally as a anesthetic. But because of the three chlorines here, that hydrogen is actually becoming fairly acidic. So if we take that and treat it with a reasonably strong base, like a T-butoxide, so the soluble equivalent of something like sodium hydroxide, we're basically getting a deprotonation. Well, again, if that happens, I'm here with, with a lone pair on the carbon again, and potentially three identical leaving groups. So most likely that happens spontaneously, because otherwise it will give me a neutral species. So I'll have something similar to the carbine that I drew to start off this discussion with, and I'll have the chloride ion. So if I take that and I react it again with a cycloalkene, I can do this with a regular alkene as well, but I'm drawing the cyclic ones just so I can show you that it does end up syn in all cases, without any real chance for rotation happening later on. So we'll get something like this happening relatively effectively. So this is a variation on the carbine thinking, but it's the same basic idea that we need the carbon to act both as nucleophile and simultaneously as electrophile. So because we still have an empty orbital here, we still have that possibility of it being an electron acceptor and using that pair of electrons as the electron donor to manage both nucleophilic and electrophilic attacks simultaneously. So that is unique for three-membered ring formation. It's a little bit easier to see here than it is for the epoxide, but the epoxide, as I said, gives us a really powerful leaving group, so that one comes up a lot more commonly, is a lot more useful in our everyday life than a cyclopropane is. But this is how we make them, and they do show up in some very interesting things. They show up in chrysanthemic acid naturally, and a lot of pharmaceuticals have cyclopropanes in them. So we do have to be able to make them, and this is the way to do it.